Please pause the video and try this problem. Okay, and now that I hope you've tried the problem, let's talk through this problem together. Now, I think you should consider this particular problem as a kind of a test of how much progress you've made on the material and the techniques so far. So I hope that you gave this problem a real shot. Remember that some of the important principles we've been trying to work on are these. We see that we don't want to wing it on Newton's second law problems and kinematics problems. There's a systematic technique for attacking these. And there's simple rules and processes that we can use to avoid overthinking it. But on the other hand, we don't want to be on autopilot because each problem can be a little bit different from the previous questions. We need to adapt our systematic process to the details of the new problem. Well, this problem here is a good test of whether you're able to carry out these three principles because there are some important differences between this problem and the previous problems in this video series. This problem has a few ways that it's different from the previous problem. So if you're on autopilot, you're going to get the problem wrong. But on the other hand, this problem is close enough to the previous questions that you should be able to use the same general systematic approach and systematic techniques, simply adapting them to the new situation. So I really hope you took your time and attacked this problem carefully, and that you tried to adapt the techniques that we'd learned before to this new problem. And if it turned out that you were able to get this question correct, that's an indication that you've made good progress on these general techniques. And if you made some serious mistakes while you were attacking this question, that's a sign that you have still some work to do as far as learning the general process and the general techniques. All right, so let's go through this problem together and see how we can adapt our general process and techniques to the differences of this particular problem. We have to choose a problem-solving framework. Here's the first two frameworks that we encounter in our class, kinematics and Newton's second law. And we decide what framework to use by looking at the concepts that are mentioned in the problem. The problem mentions mass, which is a concept that fits into Newton's second law. Here's a mention of force, which fits into Newton's second law. They mention friction, which is a force, so that fits into Newton's second law. So there's some concepts that fit into the Newton second law framework. On the other hand, they also mention beginning at rest, which is a reference to velocity. That doesn't fit into Newton's second law, that fits into kinematics. They mention some positions, which allows you to calculate distances, and again, a concept of a distance would fit into kinematics, not Newton's second law. The question's asking about speed, which is related to velocity, which is again not a concept from Newton's second law, it's a concept from kinematics. So there seem to be both concepts for kinematics and Newton's second law, so we should use both of those approaches, both the kinematics and the Newton's second law approach. Now, what type of kinematics are we going to use? Two common types would be general one-dimensional kinematics and projectile motion. Is this problem projectile motion? No, because projectile motion is when the only force on the object is the force of the Earth's gravity. That is, projectile motion is when the only force on the object is the force of the object's weight. But there's a number of other forces on this block besides its weight. So this will not be projectile motion. Instead, it's going to be general one-dimensional kinematics. I'm calling it general because it's not projectile motion. And it's one-dimensional because the object will be moving in a straight line. The object will be moving in a straight line. In this case, the object will be moving vertically, in a vertical straight line. That's one-dimensional motion. And we've discussed in previous videos the link between kinematics and Newton's second law is acceleration. So our plan is to use kinematics to find acceleration and then plug into Newton's second law, or maybe vice versa. Use Newton's second law to find acceleration and then plug into kinematics. But we need to think in terms of components. Are we trying to find ax or ay? Well, remember the components are defined relative to axes. So now would be a good time to choose our axes on this problem. And remember that you generally want to choose axes that point in the object's direction of motion. Well, this object is going to be moving up the wall. I think they said here that, well, it's implied by the wording that the object is going to move up the wall. First of all, the object began at rest and then got pushed up. Beginning at rest and being pushed up would cause the object to move up. And on top of that, the question is asking what happens when the block reaches the top of the wall, which implies that it's moving up the wall. So we should choose a positive direction pointing up the wall. I've chosen a positive y direction pointing up the wall because the object is moving up the wall. And then, for lack of a better choice, the conventional positive x direction on these problems is to the right. So I chose to the right as the positive x direction. Now, because this object is going to be moving vertically, the acceleration that's going to be relevant to our one-dimensional kinematics will be a sub y. So here's our first example of how we don't want to be on autopilot for this problem. In the previous problems, the link between kinematics and Newton's second law was a sub x because the object was moving parallel to the x-axis. But in this problem, the link is going to be a sub y because the object is moving parallel to the y-axis. In a lot of the previous questions, we've chosen diagonal axes in order that one axis would be parallel to the inclined plane. But clearly this is not this type of problem. In this case, the block is not moving parallel to an inclined plane, it's moving vertically. So we want to choose a vertical axis and then a perpendicular horizontal axis. Okay, so we've decided that our frameworks are going to be general one-dimensional kinematics and Newton's second law linked up by determining a sub y. Here's our Newton's second law approach. We want to make sure we have a sketch of the object. We were already given a sketch, but we can add the velocity vector to this sketch. That you label each vector arrow. So I'll label this vector arrow that I just wrote down as the velocity vector. And the way I determined that is, as we already mentioned, this object is going to be moving up the wall. Reading the problem carefully, it says that the object is moving up the wall, and therefore the direction of motion should indicate the direction of the velocity vector, and that should be up. And we can start adding some other stuff to our sketch here right from this point. So we can say that one key point in time is the point in time that they've mentioned here in the problem, t sub 0, which I'll set is equal to 0. And the next key point in time is when we reach the top of the inclined plane, which I'll call t sub 1. We can start building information from the problem into our sketch. The block began at rest, so that we know that originally the velocity was 0. So the velocity started at 0, and then after that it was an upwards velocity. The object started 0.6 meters above the floor. So I've taken the distance information from the problem and built it into the sketch. So first of all, we were given this distance information of 0.6 meters. Now, anytime there's distance information, you should try to build that into your sketch, and also try to make every distance starts somewhere and ends somewhere else. So try to make it very clear where your distances start and stop. For example, we know that the top of the block begins 0.6 meters above the floor. So this distance, we could say, starts at the floor and ends at this position at the top of the block. So I've labeled where that distance started and stopped. Similarly, we were given this 1.8 meters. Where does that start or stop? Well, the wall is 1.8 meters high. That tells us that that distance starts at the floor, where the wall begins, and ends at the top of the wall. So build the distance information into the sketch and build it in clearly with clear lines to show you where it starts and stops. So what I'm saying is that, for example, this would be a much less useful way to build that distance information in. Do you see that just kind of putting these numbers so they're vaguely floating out here next to the picture, that doesn't clearly show you what distances these numbers refer to. So take your time and have a nice, large, clear sketch where you show exactly where each of the distances starts and stops. Notice how I added reference lines to make it clearer where the distances started and stopped. That's a technique that you can use in your own sketch. So don't rush through this part of the problem. Make a nice, clear sketch. All right, so we made a sketch of the object and its surroundings, and we started already building the distance information into the sketch, and we drew the velocity here. So we're kind of bouncing back and forth between the Newton's second law handout and the general kinematics handout, which refers to things like building any given distance information into your sketch and labeling the key points in time. And we can also label that the path of the object starts here and ends here. So this is the path of the object, beginning here and ending here. That's something else that's useful to label for our general kinematics approach. Draw the object's path. So when we're using two different frameworks, both kinematics and Newton's second law, we kind of just have to bounce back and forth between these methods. There's no one right order that's the best to do all these steps. You try to make sure that at some point you're doing each of these steps when it seems convenient. All right, we should identify the question with a question mark and a symbol. And let's actually build that into the sketch if we can. Now the question refers to the block's speed. Now that's a technical term in physics. You should be familiar with the idea that the speed is the magnitude of the overall velocity vector. So I'm going to write down a question mark, and we want to find the correct symbol. Well, we're trying to find the magnitude of the velocity vector. That's the speed. Now let's be specific. We want the speed when it reaches the top of the wall. That's what we've called T1. So that's going to be V sub 1. V sub 1 will be the magnitude of the velocity at time 1. Well, this is something we can build into our sketch. We can write that in this location next to time 1 to indicate that we're trying to figure out the object's speed at this point. Again, this symbol stands for the magnitude of the overall velocity at time 1. That's what they mean by the object's speed. This is referring to time 1 when we reach the top of the wall. So try to write down a question mark for what the question's asking you. Try to build the question when possible into your sketch. And try to identify a specific symbol. Try to identify a specific symbol that represents what the question is asking you for. So I identified the question with a question mark and a symbol and built it into our sketch. Let's check that the given units are SI units. Kilograms are SI units for mass, newtons are SI units for force, meters are SI units for distances. Here's another SI units of meters. It looks like everything is in SI units, so that's good. This step is not applicable because we're working on a numeric problem. So we can start our free body diagram by identifying the object. Well, the thing whose mass was mentioned is the block, so that's going to be the object that we're focusing on. And we're going to focus on that block during the interval between time 0 and time 1, during the interval when it's at 0.6 meters and when it reaches the top of the wall. So that's our interval of time. The object is we're paying attention to is the block while it's moving from 0.6 meters up to the top of the wall. Now we start the free body diagram by drawing a vector for the object's weight. All right, and here's when, again, we don't want to overthink it. We want to use our simple rules. There's a simple rule for the direction of the object's weight. The simple rule is that the object's weight points down. So even though this problem looks a little different from the previous ones, we're still going to say that the weight is pointing down. Here's a dot to represent the block. Here's a downward vector to represent the block's weight, and we have to label each vector. So that gets labeled with a lowercase w for weight. That's the simple rule. The direction of the weight is down. All right, now continuing, remember we don't want to wing it. There's a simple process for completing the free body diagram, which is to ask what is touching the object. So let's take a look at the problem. What is touching the object? Well, the first thing we notice is that Jessica is pushing the block, which implies that Jessica is touching the block. So Jessica can exert a force on the block because she is touching the block. And in fact, we have information about that she's exerting a force of 210 newtons at an angle of 32 degrees, and that force is actually already drawn for us in our original sketch. Here was Jessica's force already drawn in the original sketch, so we simply need to transfer that force to our free body diagram. So I've copied this force vector from this picture over to the free body diagram, showing its direction as well. Now we need to label every force vector. So what would be a good label here? I think I'll use the label. Remember, the general symbol for force is capital F. So I think maybe I'll call this capital F sub J, because this is the force being exerted by Jessica. So capital F sub J. Now, actually, I think what a lot of professors would do is they might call it the applied force, because it's the force that Jessica is applying to the block. So if you wanted to call this the applied force, that would be perfectly okay. I guess I prefer this because it's J is one letter and APP is three letters. So this just makes the subscript a little bit easier to work with. So oftentimes in the answer key you would see this called an applied force, but I'll just call it the force that's being exerted by Jessica. Okay, so notice we already knew the direction of the force being applied by Jessica because that was given to us in the problem. Its direction is represented by this angle of 32 degrees. Now continuing, we have to ask, is there anything else touching the block besides Jessica? Well, we know the block is being pushed up a wall, so we know the block is touching the wall. The block is touching the wall. Now the wall is a surface, and we know that surfaces exert normal forces. So we're going to have to figure out the normal force being exerted by the wall on the block. Now again, this is where you have to adapt because we haven't ever seen a normal force exerted by a vertical surface before. But remember, don't overthink it. There's a simple rule. What's the simple rule for figuring out the direction of the normal force? The direction of the normal force is perpendicular to and away from the surface that is touching the object. Well, perpendicular to the wall and away from the surface of the wall that's touching the object would be to the left. This to the left is perpendicular to the wall, and this is the direction that is pointing away from the surface of the wall that's touching the block. So the direction of the normal force here would be to the left, and we need to add that to our diagram. Here's that normal force. Remember to label each force vector, so that gets labeled with a lowercase n for normal force. To the left, which is perpendicular to and away from the surface of the wall that's touching the block. So that's a good example of how we don't want to be on autopilot. There are many questions where the normal force points up, but obviously you can't assume that the normal force is always up. Obviously the normal force is not directly up for an inclined plane problem, and clearly the normal force doesn't point up in this problem. The normal force points to the left. So all the previous questions that we've tried, the surface was under the object, in a sense, a floor or an inclined plane under an object. But in this case, the surface is to the side of the object, and so that affects what the direction of the normal force is. Did you get that right? Were you able to adapt to that? This is a good test of whether you're adapting the simple rules to new situations. Even though none of the previous problems had a normal force that pointed to the left, I still hope you were able to figure out that the normal force was to the left in this problem by applying our simple rules. By the way, my experience is that I notice sometimes students want to call this force a normal force. Sometimes students want to call any force or all the forces or any unusual force a normal force. But we don't think of Jessica as a surface, so to speak, that's in contact with the block. So we're not going to think of Jessica as exerting a normal force. We just say that Jessica is exerting her own pushing force, which again sometimes is called an applied force. All we really need to know about Jessica's force is that the direction was already given in the problem and the magnitude was given as well. But we would not refer to this force exerted by Jessica as a normal force because we don't think of Jessica as being the type of thing that we consider a surface that's in contact with the object. On the other hand, the wall would be considered a surface that's in contact with the object. I haven't ever really defined exactly what a surface is. Hopefully you have an intuitive feel for that. Here on our forces handout, we have a list of the types of things that we typically treat as surfaces on problems. So some typical surfaces are things like floors, tables, walls, and inclined planes. Of course, for this particular problem, we're dealing with a wall. So I hope that this list will give you an intuitive feeling for the types of things that we treat as surfaces. These are the types of things we would say exert a normal force. Things like the things in this list are the types of things that we would treat as surfaces that exert normal forces. But in general, I hope that by doing these problems, you'll just kind of get an intuitive feel for the types of things that we treat as surfaces that exert normal forces in these types of introductory physics problems. Now, remember that whenever we assign a normal force, we also have to consider a frictional force from the same surface. And we know there is friction in this problem because it was mentioned in the problem. So now we need to use a simple rule to figure out the direction of the frictional force. Well, remember that the direction of the frictional force should be parallel to the surface and opposite to the direction of sliding. Remember, the wall is our surface, which is vertical. So the frictional force will be vertical. The block is sliding up. The block is sliding up, so opposite to the direction of sliding would be down. So our frictional force will be down. This will be kinetic friction because the block is sliding. Because the block is sliding, we're going to use kinetic rather than static friction. And the direction of the static friction is parallel to the surface and opposite to the direction of sliding. In this case, we're sliding up, so the direction of the kinetic friction is down. So let's add that to our free body diagram. So I've added a downward force for the kinetic friction, and we have to remember to label that. So again, you can see that it's important not to be on autopilot. We haven't done any previous problems where the friction was vertical. But that's just because we haven't done any previous problems where the surface was vertical. This is the first time we've seen a vertical surface, and therefore this is the first time that we've seen a vertical kinetic friction force. So we simply need to adapt our simple rules to the details of this new problem. Now, are there any other forces on the object? Well, is there anything else that's touching the object? And no, I don't think so. The two things that are touching this object are the wall and Jessica. So we've included the force from Jessica, and we included the two forces from the surface of the wall, the frictional force and the normal force. Okay, so we applied our normal approach here of completing the free body diagram by considering each thing that is touching the object. I believe this is only the second problem where we had a kind of applied force being applied directly by a person pushing on an object. So we had to adapt to that. That should have been pretty easy though, because that force was actually already drawn for us in the picture. So here's some of the simple rules that we adapted here. There's a simple rule for the direction of the weight force. The direction of the weight force is down. So we didn't overthink it, we just said the weight force is down. Here's the simple rule for the direction of the normal force, perpendicular to and away from the surface that is touching the object. So in this case, that direction was to the left. The normal force pointed to the left, perpendicular to and away from the wall. Remember, there are some problems where the normal force points up, but you certainly should not assume that the normal force always points up. This was a case where the normal force pointed to the left, so we had to adapt to that. And here's our simple rule for the direction of the kinetic friction, parallel to the surface and opposite to the direction that the object is sliding. In this case, that direction was down. Let me remind you of the logic here for the normal force. Remember, the purpose of the normal force is to prevent the object from moving through a solid surface. Well, in this case, Jessica's pushing force is trying to push the object to the right into the wall. Jessica's pushing force is trying to push the object to the right into the wall, and so the normal force has to push away from the wall to prevent the object from moving through the solid surface. That's why the rule makes sense. That's why the rule of pointing for the normal force to point perpendicular to and away from the surface makes sense. That's the direction that's required to prevent the object from moving through the wall to the right. You don't have to think it through in that much detail, though, necessarily, that you can just use this rule, perpendicular to and away from the surface that's touching the object. Remember, that's what normal means. Normal means perpendicular. In this case, perpendicular to the surface. Now, let's remind ourselves of this idea from the forces handout. Every force is exerted by some object on another object. So, as an exercise to improve our understanding of the material, let's try this exercise. Every force is exerted by some object on another object. So for each of the problems in our free body diagram, pause the video and identify what object is the force being exerted by and what object is the force being exerted on. I hope that you'll pause the video and try this exercise for each of the forces in the free body diagram. I hope you actually gave that a shot, and now let's look at some answers. Okay, here are the answers, so you can check whether you got these correct. Did you realize that the weight force is being exerted by the Earth on the block? How can the Earth be exerting a force on the block if the Earth is not touching the block? Well, that can happen because the weight force is a gravitational force, and a gravitational force can be exerted at a distance. So the weight force is the gravitational force exerted by the Earth on the block. All the remaining forces are being exerted by objects that are touching the block. So Jessica's applied force is the force that's being exerted by Jessica on the block. The normal force is the force that's being exerted by the wall on the block. And the frictional force is a second force that's being exerted by the wall on the block. So notice that surfaces can exert two forces. A surface can exert both a normal force and a frictional force. A surface can exert both, like a wall, a surface like a wall can exert both a normal force and a frictional force. The normal force is the force that the surface exerts perpendicular to the surface. And the frictional force is the force that the surface exerts parallel to the surface. Notice that every single one of these forces was being exerted on the block. This force is being exerted on the block, this force is being exerted on the block, this force is being exerted on the block, and this force is being exerted on the block. Well, that's no coincidence, because remember, the whole purpose of this free body diagram is to show only the forces that are being exerted on the block. For example, in this free body diagram, we would not want to include any of the forces that were being exerted by the block. The purpose of this diagram is only to include the forces being exerted on the block. So we reviewed here that the weight force is the gravitational force exerted by the Earth on an object. An object's weight is the gravitational force exerted by the Earth on that object. The normal force is the force exerted, is one of the forces exerted by a surface on an object. And a friction force is another force, a second force that's exerted by a surface on an object. I haven't been going through this exercise for every single problem that we've been working on, just because the video explanations have been long enough even without this, but this is a useful exercise for you to try on your problems. It's useful after you've written a free body diagram to try this exercise to help you build your understanding of this material. So let me ask you, did you get this free body diagram correct on this problem? If you got the free body diagram correct, fantastic. That shows that you've made excellent progress on free body diagrams. If you got this wrong, you need to figure out what went wrong and try to fix that on future problems. For one thing, take your time on the free body diagram, especially when the problem's a little bit different from the ones you've seen before. There's no point rushing through the free body diagram, because if you make one little mistake on the free body diagram, all the rest of your work on the problem will be useless. It's impossible to get a question right if your free body diagram is wrong. So do not rush through the free body diagram. Take your time. Take your time while drawing the free body diagram and try to get every detail correct. Because unless every detail is correct, you won't be able to get the rest of the problem right. That's especially important when the problem is a little bit different than the problems that you've seen before. Okay, well, we took our time, but now we're ready to move on. Remember, something else we used here is that anytime you see a surface exerting a normal force, you should also consider the frictional force. So the surface of the wall here exerted a normal force, and we also identified the frictional force from that wall. Now we're ready to move on to our force table. So we have the force of the weight. And remember, don't overthink it. There's a special formula for the magnitude of the weight. Here's our special formula for the magnitude of the weight. Our mass is 12 kilograms. Little g is 9.8. Of course, we always plug in a positive number for little g, because little g stands for a magnitude. The magnitude of the acceleration due to the Earth's gravity. Now we can do our calculation. 12 times 9.8. That comes out to be 117.6. Make sure you put the units on that. So remember, what does this stand for? I hope you didn't say this stands for the weight. It doesn't stand for the weight. It stands for the magnitude of the weight. That's an important distinction. And now that we have that magnitude of the weight, we can figure out the x and y components for the weight. Well, the weight force points down, so its x component is 0. And of course, remember that we're using these axes. Components are always defined in terms of your axes. The weight force is down, so the y component of the weight is pointing in the negative direction. And the magnitude will be 117.6. The overall magnitude is the same as the magnitude of the y component because the x component was 0. We've seen some problems where we had a weight component that was positive and some problems where we had a weight component that was negative. So don't be on autopilot, just figure out for each problem whether each relevant weight component is positive or negative. Here we ended up with negative based on the axes that we've chosen. Now that we've handled the weight, why don't we move on to the normal force. Now, we don't have any special formula for the magnitude of the normal force, and we don't know a number for the magnitude of the normal force. So we'll simply follow our normal practice of representing the magnitude of the normal force by this symbol, lowercase n. And we'll use that symbol to break the normal force into components. Now, our normal force is horizontal. It's anti-parallel to the x-axis, so there's 0 y component. There's 0 y component for the normal force. The normal force here is pointing in our negative x direction. So our normal force x component will be negative. And the overall magnitude will be the same as the magnitude of the x component because the y component was 0. So again, this is a good example of how we don't want to be on autopilot. I think that in all of our previous problems, I think that we got that the x component of the normal force was 0 and the y component was positive n. I think this was the pattern in some or all of our previous problems, but don't be on autopilot. We had a different pattern here. In this case, there was 0 y component and the x component was negative. That didn't match our previous pattern, but That's what we got when we just applied our simple techniques and approach to this direction and these axes. So simply respond and adapt to the details of the question that you're working on, rather than just trying to memorize what the normal force will come out to be for each individual problem. Notice that although we have to adapt to the new details of this problem, we're certainly not overthinking it. There's no kind of deep philosophical thoughts that we have to go through to get these new values for the normal force. We simply adapt to the same thought process that we've used on the previous problems to the new details of this problem. So adapt, but don't overthink it. Okay, so that's how we would handle the normal force here. Then we have the kinetic frictional force. Now there's a special formula for the magnitude of the kinetic friction. Mu k times little n. So first I'll write the general formula and then I'll plug in. Mu k we were given as 0.3. Mu k was 0.3. Remember that you have to be willing to keep going back and rereading the problem to extract the data that you need from the problem. We don't know what little n is, so we'll continue to represent that by little n. So now we have that expression. First we wrote the general formula, then we plugged in. We did that off to the side so it wouldn't mess up our nice clean force table, and then we wrote our final result here in the force table. So here we've gotten a mathematical algebraic expression that involves a number and a symbol. But we won't let that make us feel uncomfortable. We should be able to use this mathematical expression to break this force into components. Now our frictional force here was vertical, so anti-parallel to the y-axis. So the frictional force has 0 x component. There's no x component for this vertical force. The frictional force points in the negative y direction, so the y component is negative. And since the x component was 0, the entire magnitude goes into the magnitude of the y component. So I simply take this value and put it here. As we've discussed in previous videos, it would be a mistake just to call this n sub y. Some students might be tempted to call the y component n sub y, use n sub y, but that doesn't make sense. If this component is 0, then the overall magnitude has to be the same as the magnitude of the y component. So avoid that mistake. Now again, I think this is a different pattern than we've ever seen before. I think that in all the previous problems, the y component of the friction was 0. But in this problem, it was the x component that was 0. So we had to adapt to the details of this new problem, but that did not involve overthinking it. We didn't have to think deep philosophical thoughts to adapt here. We simply adapted the standard simple rules and thought processes that we've used on the previous problems. Okay, now make sure that you include all the forces. We also have the force exerted by Jessica. Now, in this case, there was a number that we were given. The problem told us that Jessica was exerting a force of 210 newtons, and that was also given to us in our sketch. So we can say that this is 210 newtons. So, what does this stand for? I hope you didn't say it stands for the force exerted by Jessica. This stands for the magnitude of the force exerted by Jessica. Remember, this would be the complete force exerted by Jessica, including its direction. Without the arrow, this symbol just stands for the magnitude of the force. Remember that our standard approach to making our force table is that the first line just represents magnitudes. The first line represents magnitudes, and the second and third lines represent the components with their plus and minus signs. No plus or minus signs in the first row because that's magnitudes. And now we need to break Jessica's force into components. Now, all of the previous forces here on this problem were easy to break into components because all of these forces, weight, normal force, and frictional force, all of them were either parallel or anti-parallel to one of the axes. But you can see that Jessica's applied force is neither parallel nor anti-parallel to either the y or the x-axis. It's making an angle with both the y and the x axes. So we have to use a different approach to break this force into components. we have to use the right triangle approach. We're going to have to draw a right triangle to break Jessica's force into components. We're not going to do that in our free body diagram because that'll make the free body diagram too messy, and I won't do it here because I don't want my main sketch to be too messy. Let's make a separate sketch just for the right triangle to break Jessica's force into components. So we're going to start that sketch, and we need to draw that right triangle. So through the tail here, I'm going to draw a line that's parallel to the y-axis. Remember that the overall vector should represent the hypotenuse, and the legs should be parallel or anti-parallel to the axes. So through this point, I'm going to draw a line parallel to the y-axis, a vertical line. That's really already been started for us. Then through the head of the overall vector, I'll draw a line parallel to the x-axis, a horizontal line. Label the sides. This side is parallel to the y-axis, so this side should be labeled as Jessica's force y component. And this side was parallel to the x-axis, so this side is labeled as Jessica's force x component. If we remember, some people would call this the applied force. So then this would be the applied force x component, and this would be the applied force y component. Any of those series of symbols would be fine. But you can see this gives us fewer subscripts. I prefer this because there's fewer subscripts to write here. You have to put the arrows on here. Well, the easiest way to do that is to say that the overall vector is pointing to the right and up. And therefore, the components should point to the right and up because they're supposed to represent the overall vector. The more technical way to think about it is that where we have the head of the overall vector, we should have the head of this component. And where we have the tail of this overall vector, we should have the tail of the component. That's this rule here. Okay, so we've drawn the right triangle. Now, of course, keep in mind we could have drawn a right triangle to the right of the vector. We could have drawn a right triangle over here to the right of the vector, but then that wouldn't include the 32-degree angle that we were given. So this is the superior triangle to draw because it includes the angle that we were given. Now I'll go ahead and shift to this symbol here and say that the magnitude for f sub j is 210 newtons. That represents the length of that side. I shifted to this symbol because now I'm just writing the magnitude. Remember that before we do the magnitudes of the components, we should do their signs. So the x component points to the right, which is our positive direction, and the y component points to the right, which is also our positive direction. Now we're ready to label this side as the hypotenuse because it's opposite to the 90-degree angle. Here's the angle that we're focusing on, the 32-degree angle that we were given. So this side gets labeled as adjacent because it's adjacent to the 32-degree angle that we're focusing on, and this side gets labeled as opposite because it's opposite to the 32-degree angle that we're focusing on. Now we can apply SOHCAHTOA. So we'll have that the sine of our 32-degree angle equals opposite over hypotenuse. And the cosine of our 32-degree angle equals adjacent over hypotenuse. Sine 32 degrees equals the length of the opposite side is the magnitude of fjx. Length of the hypotenuse is 210. Cosine 32 degrees equals length of the adjacent side is the magnitude of fjy. And the hypotenuse is 210. Multiply both sides by 210 to get the variable by itself. So the calculation is 210 times sine of 32 degrees. I'll round that off to 111.3 since this is an 8. Remember to put the units in now that we've finished solving that equation, and fjy will be 210 cosine 32 degrees. I'll round that to 178.1 since that digit's a 9. Now, these absolute value signs are supposed to remind us that the SOHCAHTOA equations only tell us the magnitudes of the components, and we need a last step in order to figure out the complete component, including the plus or minus sign. We already worked out the signs. Fjx is positive. And f sub jy is also positive on this problem. Now we should build these numbers back into our sketch so we can check if they make sense. So I've taken these numbers and built them back into the triangle, and now let's use these principles to check if our results make sense. Is the longest side the hypotenuse? Yes, 210 is longer than these other two sides. And you can see this 32-degree angle, that's the smaller of the acute angles. We haven't calculated this angle, but it should be obvious that this angle, since the 32 is less than 45 degrees, this angle is bigger than 45 degrees. So this bigger acute angle is opposite the longer side, longer leg of 178. And the smaller acute angle, 32, is opposite the smaller side of 111. So this also checks out. That is also principle also matches our sketch. So yes, it looks like we broke this vector into components correctly. Now notice that for this problem we used cosine to find the y component. That should have read like this. We use cosine to find the y component, and we use sine to find the x component. But don't be on autopilot. We've also seen other problems that followed a different pattern. Do you remember this problem? This was a problem we did a while ago back in this series. Well, if you remember this problem with the block being pulled by the rope, notice here we used cosine for the x component. Here we used cosine for the x component, whereas for the problem that we're just working on, we used cosine for the y component. So you can't memorize that cosine is used for the y component or that cosine is used for the x component. You have to you just have to use the general principles for SOHCAHTOA. If you go through the general steps for SOHCAHTOA, the algebra will figure out for you whether you should use cosine for the y component like we did on this problem, or whether you should use cosine for the x component like we did on this previous problem where the object was being pulled by the rope. So you don't necessarily have to write down all of these steps, but you need to write down or think through enough of these steps so you can determine whether to use cosine for the x or y component and whether to use sine for the x or y component, and whether you should be multiplying or dividing by sine or cosine. In these problems we multiplied by sine and cosine, but we did see one other problem where we used SOHCAHTOA where we divided by the sine. So do enough of the SOHCAHTOA steps so that you can adapt to the details of the problem that you're working on. Don't assume that you can just be on autopilot. Don't assume that the calculations for SOHCAHTOA will be the same from one problem to the next. They're often the same, but sometimes they're different. Identify the hypotenuse, opposite, and adjacent sides in your right triangle and set up the algebra, and then the algebra will tell you what the right way to calculate the components is. So here we have f sub jx is 111.3. Newtons, and f sub jy is positive 178.1. Newtons. Did you get these components correctly? If you got these components correct, excellent. If you got these components wrong, that's not so good. Then you need to keep working on getting to the point where it's boringly easy for you to find the components correctly. If you got these correct, then maybe you can start to skip some of these steps or do some of these steps in your head. But if you got this incorrect, you need to keep writing out all of the SOHCAHTOA steps on paper until you're getting the problems that part of the problem 100% correct, and until those parts of the problem are boringly easy for you. Okay, so now I think we have our force table. All right, so did you get this force table correct? I hope you got the force table correct. I hope you can see that there were some ways the force table was different from the previous examples, but not in the general principles. We used the same general principles in this force table as we've used in the previous force tables. Notice that all the non-zero components have either plus or minus signs in front of them. Make sure there's a plus sign in front of all of your positive components, and then you're going to remember when you need the negative sign in front of the negative components. If you left out this negative sign, or this negative sign, or this negative sign, then I think you got the problem wrong. So make sure that you're thinking about the plus or minus signs carefully when you do this table. This table illustrates three different possibilities. Sometimes you're given a value for a magnitude. That's the case here. We were given a value for the magnitude of F sub j, 210 newtons, so we just used that value. Sometimes you're not given a value, but you have a special formula for the magnitude, and that was the case here and here. We had special formulas for the magnitude of the weight and the magnitude of the kinetic friction. Remember that these formulas only tell us the magnitudes. It was our job to figure out the plus or minus signs in the components. And then the third case, sometimes you're not given a value and you don't have a special formula, and then you just represent the magnitude with a symbol. And that was the case for the normal force. We just represented the magnitude of the normal force with a symbol. Some of the details in this problem were different than earlier, but hopefully you could see that you didn't have to overthink it. You could use the same general principles to get the correct results in your force table. Most of the problems that we've been doing up till now, I think, had three forces. I think this might be the first problem we've done that had four forces. This might be the first problem that we've done that had four forces in the problem. So it's especially important to be organized. For example, just don't forget any of the forces. Sometimes I see people do the free body diagram correctly, but then they just forget to include one of those forces in the force table. So remember, don't leave the force table until you've just counted and made sure that you've dealt with all the forces from your free body diagram. Our free body diagram had 1, 2, 3, 4 forces, so make sure that you have 1, 2, 3, 4 forces in your force table. Check to make sure that you haven't left one of the forces behind when you get to the force table. Did you get this force table correct? If you didn't, maybe it's because you were going too quickly. Remember, take your time with the force table. Take your time. Don't be in a rush to get to the Newton's second law equations. Take your time with the force table, because if you make one little mistake in your force table, all the rest of your work will be useless. On these long multi-step problems, you're not going to be able to get full credit unless you take your time and double check your steps for the free body diagram and the force table. Be tough on yourself and don't aim for partial credit, aim for full credit. Aim for 100% credit, especially when you're just doing practice problems in the homework where you have enough time to really take your time and double check each step. So don't rush through the force table. Make sure you're getting all these details correct. Of course, if you find that you're always getting the force tables 100% correct, then you can afford to start speeding up. But if you're one of the many students who oftentimes makes a little mistake in the force table, then try to force yourself to slow down and double check your work and avoid those mistakes. And of course, we're trying to keep our free body diagram and a force table as neat and clean as possible. The more forces there are, the more important it is to be well organized. Okay, so we've dealt with these steps in our approach. We're ready to move on. Notice that it didn't cause us any problems that we had a mathematical expression here for F sub k. We just used that mathematical expression to break this force into components. There was no problem. Even though this was partly a number and partly a symbol, we were still able to use that expression with partly a number and partly a symbol to break that force into components. Now, before we move on to the Newton's second law equations, let's remember that we're also planning to apply general one-dimensional kinematics to this problem. Now's a good time, now that we've finished the preliminary steps for the Newton's second law approach, now's a good time to do the preliminary steps for the general one-dimensional kinematics approach. So let's shift over to our general one-dimensional kinematics handout. We've seen there's two different types of kinematics we might apply: simple kinematics involving constant velocity, or the more common and typical type of kinematics that involves constant acceleration with changing velocity. So we have to decide which of those applies for this problem. Well, we know that in this problem, the object begins at rest. We know that the object begins at rest and then begins moving. But that means that the velocity is changing. If the object begins at rest and then starts moving, that means that the speed changes. The speed starts at 0 and then increases. But the speed is the magnitude of the velocity. So if the speed is changing, then the velocity is changing. So because the block begins moving from rest, we know this is a problem with changing velocity, not constant velocity. And we know the acceleration is constant because the acceleration is determined by the forces. Well, in this problem, the forces are constant, so the net force is constant, so the acceleration is constant. We have no reason to think that any of these forces from our force table is changing. To be more specific here, we know that the weight is constant. The weight has a constant magnitude of 117.6 newtons. And we know that Jessica's applied force is constant. She's applying a applied force of 210 newtons. The problem implies, well, actually it states explicitly, the problem states explicitly that Jessica's applied force is constant at 210 newtons. So we know that the weight and the applied force are constant, and the normal force and the friction will adjust in response to the weight and the applied force. So we can expect that the normal force and the frictional force will also be constant on this problem. So in this problem, we can expect that the forces will be constant, which means the net force will be constant, which means the acceleration is constant. So we've determined that this is a problem with constant acceleration and changing velocity. We used the idea that the acceleration is constant when the net force on the object is constant. We've already discussed the object in the interval of time earlier, so the object that we're going to apply Newton's second law and the kinematics equations to is the block during the interval of time between time 0 and time 1, the interval between when the block begins moving and when it reaches the top of the wall. We've already seen that the units on this problem are SI units, which guarantees that they're consistent units. This step is not relevant. We've already worked with the sketch, and we've already built the key distance information into our sketch. That's important, but we've already done that. Let's see, we've already written down our key points in time, and we've already set time 0 equal to 0. I don't think we were given any time information, extra time information that we could build into our sketch. We've already written down our axes. We've already identified the question. Here's an important step. We should label the initial and final positions on the path. Well, we've already decided that the two key points in time on this problem are time 0 here, so I'll call that the initial point, and t1 up here, which I'll call the final point. These, the initial and the final point, are the 2 points that you're going to plug into your kinematics equations. Let's see, we should plug this point in time into our kinematics equation because we know stuff about it. For example, we know that the velocity at this point is 0. And we should plug this point into our kinematics equations, for one thing, because this is what the question is asking us about. I encourage you to actually write down an I and write down an F to explicitly label in your sketch which is the initial and which is the final point. For example, here it's useful to notice that we don't really care about this point in time. Well, we don't care about this point on the wall at all. Nothing interesting is happening here. The block's never going to be here. So labeling the initial and final points helps us to see where the block is starting and stopping. In this case, these are the two key points in time we're going to plug into our kinematics equations. So we completed this step. So now we've completed all of the preliminary steps for general one-dimensional kinematics, just as we earlier completed the preliminary steps for Newton's second law. Now we can move ahead and write down the general Newton's second law equations. So we'll write the general formulas. Sum of the forces X equals MAX. Sum of the forces Y equals MAY. We've completed this step, and now let's bounce over to the general kinematics approach and write down our setup for kinematics. Remember, we decided on this problem we're applying constant acceleration with changing velocity. So we'll use this right-hand column of the handout, and the setup is to write down the 5 kinematics variables. But here's where we have to be careful not to be on autopilot. Remember that on this problem, the object is moving in the y component, not in the x component. So on this problem, we're going to use the y variables for kinematics, not the x variables for kinematics. So be careful to write down the exact right symbols, specifying that here we're focusing on the y components variables for kinematics in this problem, because we're moving in the y component. The object is moving vertically this way in the y component. Delta t. We're applying one-dimensional kinematics to the y component because we're moving vertically parallel to our y-axis. So in the past, I would have used delta x for the displacement, but don't be on autopilot. Don't be on autopilot. Now we should use delta y, right? We should use delta y now for the displacement, because we're being displaced parallel to the y-axis, not the x-axis. So then this variable will be v initial y, and we have v final y and a sub y. So don't be on autopilot. In the previous problems, we focused on the x component for our kinematics. But on this problem, the object is moving vertically parallel to the y-axis, and therefore, here's the path, vertical path. So we should be focusing on the y component for our kinematics, not on the x component. For Newton's second law, we're using both the x and the y components, because we're going to have forces with both x and y components. But for kinematics, we're only focusing on the y component because the object has no motion in the x component. Did you notice that when you were doing the problem? Did you notice that you had to do kinematics for the y component rather than the x component? Don't be on autopilot. All right, so now moving through here, we can start plugging in. Wx plus nx plus fkx plus capital F jx equals max wy plus ny plus fky plus capital F jy equals may. Keep in mind that in physics there's a difference between lowercase and capital letters. We're using lowercase f for friction and capital F for the applied force applied by Jessica. Be careful with your uppercase and lowercase and capital letters. Try to always use the exact right symbol with the exact right subscripts. Exact right symbol with the exact right subscripts. Exact right symbol with the exact right subscripts. Take your time. Take as much time as is necessary to use the exact right symbol with the exact right subscripts. That's the way to build your physics skills so that you can keep adapting to harder and harder problems. All right, so our delta t, I guess we don't know that, do we? We don't know the delta t on this problem, so we'll just call that delta t. How about our delta y? Now, exactly what distance here represents delta y? Is delta y going to be this distance from here to here? Is delta y going to be this distance from here to here? Where exactly is delta y? Well, the delta symbol here reminds us that we're thinking about the change in position between the initial and final points. The delta refers to a change between the initial and final points, so this is where it's helpful that we've labeled our initial and final points. Remember that we labeled that this point here will be our initial point on the path, and this point here will be our final point. And therefore, delta y is neither of the two distances I outlined before. Instead, delta y is going to be this distance. Delta y will be this distance, or to put it better, delta y will be this directed distance from here to here. When we're determining the displacement, we should be determining the displacement between the point that we've chosen as the initial point and the point that we've chosen as the final point. So now we should carefully build that into the sketch. We should build into the sketch that this is the distance that we'll be using as our displacement. Delta y will be this distance from here to here. So based on all the information we've built into the sketch, it should be clear that this distance, well, let's work out the direction here. Remember, this is a component, the y component of the displacement, so we should figure out the plus or minus sign first. Well, we're starting here and we're moving in the positive y direction up to here. So delta y will be positive. And I'm going to put an arrow here. And I'm not going to put an arrow here. The displacement is a directed distance. The displacement is this directed distance from here to here. So I'll put the arrow only on this side to show that we're moving from here to here in the positive direction. Figure out the sign before you do the magnitude. All right, and then I think it should be easy to see that if this distance is 1.8 meters and this distance is 0.6 meters, then this distance should be 1.8 minus 0.6. The advantage of building all this information into the sketch is that it should make clear that this distance from here to here is 1.8 minus 0.6. So that's 1.2 meters. So build the numbers that you're given into your sketch and also build what you're trying to figure out into the sketch, and that will help you to think correctly about the geometrical relationships. So our delta y is positive 1.2 meters. We can put that into our framework here. Positive 1.2 meters. Did you get that right? That should have been a pretty easy part of the problem. If you didn't get that right, it might be because you're not doing a good enough job to make a large, clear sketch with all the information. So if you got that part wrong, make larger, clearer sketches and build more of your information into your sketch. So notice in this problem, we were given the numbers 1.8 meters and 0.6 meters. And it might be tempting to plug either of these numbers into the kinematics equation as the displacement. But neither of these is the correct displacement. They're both traps, so to speak. Displacement is in meters, but these are not the right values in meters. The correct displacement is the positive 1.2. So I've talked about this trap in the past. Just because you're given a number in the correct units in the problem doesn't mean that's the right number to plug into your equation. So be careful. We didn't ignore these numbers. We used them to figure out the 1.2 meters, and that's the correct number to plug into the kinematics equation. Again, drawing a clear sketch is the right way to see what the right number is to plug in for displacement. So our v initial y, we've already seen that the object is starting from rest. Since the object is starting from rest, its initial velocity will be 0. So the initial y component of the velocity will be 0. How about v final y? Well, that's what we need to answer the question. we need to figure out v final y in order to answer this question, because the question is asking about the final velocity, the velocity at time 1. So I can't write down a number here, but I can write down a more specific symbol. The general symbol for this concept is v sub fy, but the more specific symbol that we can use for this problem is v sub 1y, because our final point is the point in time we've labeled time 1. So we want to know the final velocity. We want to know the y component of the velocity here at time 1. That's what we need from our kinematics equations. And a sub y, we don't know. A sub y, we don't know here yet. Again, we could say that's something that we are going to need, because remember, a sub y is going to be our connecting link between kinematics and the Newton's second law equations. Okay, so now we've also labeled what we needed from kinematics. We've written down specific numbers and symbols for the variables in kinematics. So now let's start working in our 3 columns, the 3-column approach to the math that we've seen before. So over here, f sub x, we can plug in 0 plus negative n plus 0 plus 111.3 and our mass is 12 kilograms. And well, I'll go ahead and put in these numbers here first. This is negative 117.6 plus 0 plus negative 0.3 n plus 178.1. Take your time and try to copy all the numbers accurately from the force table. Try to avoid careless mistakes. The mass was 12 kilograms. Now, what's a sub x? Well, this object is motionless, as we've said, in the x component, and therefore a sub x is 0. Why don't you pause the video and write out the logic? Why is a sub x 0 in this problem? Well, we know that the object is motionless in the x component. And that means that v sub x is constant at 0. And that implies that a sub x is 0. Not because v sub x is 0, but because v sub x is constant. It's the constancy of v sub x that makes a sub x 0. If vx is 0, ax does not have to be 0. Just because velocity is 0 doesn't mean acceleration has to be 0. But the acceleration is about the change in the velocity. So when the velocity is not changing, the acceleration is 0. Here are the rules. If the velocity vector is constant, that's when we know the acceleration vector is 0. That's what we have here. Vx is constant, and therefore ax is 0. Version of that rule that's a little bit more relevant, because this is specifically... oh, I guess I didn't quite print that correctly. Okay, here we go. In this case, we have that Vx is constant. Vx is constant, and therefore Ax is 0. And that's what we have here. Vx constant, so Ax is 0. Vx is constant, so Ax is 0. Okay, you don't have to think that through so carefully every time, but it's good to be able to occasionally do that. So our a sub x is 0 in this case. How about a sub y? Well, we just don't know what a sub y is, so we have to continue to just write that as the symbol, a sub y. Remember, a sub y is going to be our connecting link between our kinematics and our Newton's second law. Can we say that a sub y is 0? No. There's no reason to think that the object is motionless in the y component. We know that it's moving in the y component. And we also know that it's not moving with constant, moving with constant speed, because if its speed was constant, it would stay at rest at the, where it started at the beginning. So there's no reason to think a sub y is 0. We just have to represent this by the symbol a sub y. So remember, think in terms of components. Our analysis for a sub x was quite separate from our analysis for a sub y. Did you get those accelerations correct? Remember, don't be on autopilot. In all the previous problems, in all of our previous problems, a sub y was 0, and a sub x was what we were trying to solve for. Because in the previous problems, the objects were moving parallel to the x-axis. But this is the first problem we've done where the object was moving parallel to the y-axis. So in this problem, a sub x was 0, and a sub y was the variable that we were trying to figure out. By the way, I should say, if you wanted to, you don't have to call this the y-axis and this the x-axis. If you wanted to, you could have called this the x-axis and this the y-axis, and then obviously our symbols would be different. This could be called x and this could be called y, but I don't recommend that. I don't recommend that because the convention is that when there's a horizontal and vertical axis, the convention is to use x for horizontal and y for vertical. So this would be possible, but is not recommended. Instead, in the answer keys, these would be the axes you'd probably see. So you might as well stick with the answer key, the axes you'll probably see in your answer key, where we follow the conventional rule when we have horizontal and vertical axes of having x be horizontal and y be vertical. And if you choose these axes, then the way I've written it out is the correct way to write out a sub x and a sub y. Remember that your results on the problem always depend on your axes, so make sure you have your axes written down. Okay, so now what was the question asking us for? It was asking us for the final velocity, which we're going to get from our kinematics approach. Velocity will come from kinematics. But remember that for kinematics, we're not ready to pick a kinematics equation until we know values for 3 variables. Remember that on this problem, we're applying kinematics, the form of kinematics with constant acceleration with changing velocity in this right-hand column. And for this form of kinematics, to pick an equation, we need to know values for 3 of the kinematics variables. Remember, the reason for that is that each of these kinematics equations has 4 variables. Each of these kinematics equations has 4 variables. So the equations are not very useful to work with until we know values for 3 of the variables in the equation. So here it looks like we have 2 knowns. We know this and we know this. But that's not enough. There's only 2 things we know. All the remaining variables are unknowns, so it would not be productive yet to pick a kinematics equation because there's not enough knowns. So we're going to need to make some progress here. Well, it would help to know a sub y. A sub y is our connecting link, and we can get that from the y equation. So we can simplify this y equation. So we made a little simplification in the y equation. Adding a negative turns into a subtraction. But notice that this equation has 2 unknowns. Little n is an unknown and a sub y is an unknown. Well, 2 unknowns is too many. So again, it's probably not going to be productive to work too much more on this equation. Well, don't give up. We've got 1 equation left. Let's take a look at this equation. We can simplify this. And notice this equation has only 1 unknown. Since this equation has only 1 unknown, this is the most likely equation for us to start with. So let's start by solving this for the unknown. How will that help us? Well, we can eventually take that little n and plug it into this equation to help us with the y equation. Well, this equation is very simple to solve. We need to get the n and the 111.3 by themselves. We could move this term to the right, but wouldn't it be more convenient to move this term to the right, because that will also allow us to get rid of the negative sign. So I'll add plus n to both sides, and that will kill 2 birds with 1 stone. It'll get the n separate from the number, and it'll also get rid of all the negative signs in the equation. Okay, I guess we're done now. We've solved this equation. So let's go ahead and put the units in here and ask if this makes sense. Well, this came out to be positive. That makes sense because this stands for the magnitude of the normal force. And magnitudes can't be negative. By the way, we know that on this problem, the x component of the normal force should be negative. On this problem, the x component of the normal force should be negative. But that does not mean that this variable should be negative, because remember, this symbol doesn't stand for the complete x component. This symbol, written without an arrow, just stands for the magnitude of the normal force. So we already took into account that the x component of the normal force would be negative by writing this negative sign. But we don't expect this number to be negative because this variable, this symbol, just represents the magnitude of the normal force. So if we had gotten a result that this symbol was negative, then we would know that we had made a mistake, because this symbol stands for a magnitude, and magnitudes should never be negative. So remember to think carefully about exactly what each specific symbol stands for. This specific symbol stands for the x component of the normal force, which is negative on this problem. But this symbol stands just for the magnitude of the normal force, which would never be negative. So the sign of this result does make sense. This result for little n came out to be positive, and that does make sense. And let's think about whether the size of this result makes sense. What should we compare the normal force to? If you haven't done so already, pause the video and ask what you can compare the normal force to see whether it makes sense. Well, remember that the function of the normal force, its reason for existence, is to prevent the object from starting to move through the wall. The normal force is pushing to the left to stop this object from starting to move through the wall. Well, who is trying to push the object through the wall? Not friction and not the weight. They're not pushing horizontally. It's Jessica who's trying to push the object through the wall. So you should not be comparing the normal force to the weight force. Don't compare the normal force to the weight force on this problem, because they are in completely separate components. The normal force here is horizontal and the weight force is vertical. There's no close relationship between them here. Instead, the only other force that's horizontal besides the normal force is Jessica's pushing force, which is partly horizontal. So compare those. Well, notice that the normal force here came out to be less than Jessica's pushing force in magnitude. So we have that this normal force is less than the magnitude of Jessica's pushing force. The 113 newtons is less than the 210 newtons. Does that make sense? Pause the video and ask if that makes sense. Well, to try to make it easier to think about this, here I've written a new version of the free body diagram where all the forces are broken into components. Earlier we figured out that the components of Jessica's pushing force point up and to the right. So in this new version of the free body diagram, I've drawn each of the components of Jessica's pushing force pointing up for the y component and to the right for the x component. Now remember that the purpose, so to speak, of the normal force on this problem is to prevent the block from beginning to move through the surface of the wall. Well, what exactly is trying to start the object moving to the right through the surface of the wall? It's only the x component of Jessica's applied pushing force. Only the x component of Jessica's applied pushing force is trying to start the object moving through the wall. The y component of Jessica's force is not trying to get the object moving through the wall, because the y component of Jessica's force is pulling parallel to the wall. So in order to prevent the object from beginning to move, the normal force does not have to cancel out all of Jessica's pushing force. The normal force only has to cancel out the x component of Jessica's pushing force. And that explains right there why it does make sense that the magnitude of the normal force came out to be less than the overall magnitude of Jessica's force. the magnitude of the normal force is less than the magnitude of Jessica's pushing force, because the normal force doesn't have to cancel all of Jessica's applied force. The normal force only has to cancel the x component of Jessica's push. And I tried to reflect that. I tried to draw this arrow for Jessica's, for the x component. I tried to draw this arrow for the x component of Jessica's pushing force to be the same length as this arrow for the normal force. Notice that the normal force actually came out here to equal the x component of Jessica's force in magnitude. The normal force is 111.3 newtons, and that equals the x component of Jessica's pushing force in magnitude. And we've seen that that does make good sense, because the x component of Jessica's pushing force is exactly what the normal force has to cancel to prevent the object from moving through the surface of the wall. Remember that the purpose, so to speak, of the normal force is to prevent the object from moving through the solid surface. So the magnitude of the normal force will be whatever it takes to prevent the object from moving through the surface. Remember again, though, that you should not really try to predict what it will take ahead of time. You should not try to predict what it will take for the normal force to prevent the object from moving through the solid surface ahead of time. That could lead to confusion. Instead, let the Newton's second law equations figure out the relationships for you. Let the Newton's second law equations determine those relationships for you. And then after you get a result, like right now is the right time to step back and ask if that relationship makes sense. You can see here how Newton's second law figured that out for us. Newton's second law knew that we needed all the x forces to cancel out to zero. And therefore, Newton's second law had to balance the normal force with the x component of the pushing force. And in order for those to balance, Newton's second law figured out that the magnitude of the normal force has to equal the magnitude of the x component of that pushing force. Notice you should not say that the normal force equals the x component of the pushing force. Don't say that the normal force equals the x component of the pushing force. Be more specific and say that they're equal in magnitude. In magnitude, they're equal. But notice that the direction of this normal force is not equal to the direction of the pushing force. It's only the magnitudes that are equal. So try to be precise in your terminology. Remember, this symbol does not indicate the direction of the normal force. This symbol only indicates the magnitude of the normal force. And that's the thing that's equal to the magnitude of the x component of the pushing force. So our analysis here, as usual, indicates the value of thinking in terms of components. By thinking in terms of components, we were able to understand why the normal force came out to be less than Jessica's pushing force in magnitude. This also shows the importance of using the exact right label for each concept and not mixing up the concepts. In our previous problems, we generally compared the normal force to the weight. On previous problems, it was useful to compare the normal force to the weight. Did you realize that on this problem, it's not useful to compare the normal force to the weight? Instead, we should compare the normal force to the pushing force. We can only think clearly about those ideas if you give everything a precise label and avoid using the word it. Avoid using the word it and give everything a precise label so that you know exactly what you're thinking about comparing the normal force to. On previous problems, it was the weight that was trying to make the object move through the surface. So it made sense to compare the normal force to the weight. But on this problem, the weight is not trying to make the object move through the surface. The weight is pulling parallel to the surface. On this problem, it's Jessica's pushing force that's trying to make the object move through the surface. At least one component is. So it made sense to compare the normal force on this problem, not to the weight, but to Jessica's pushing force. Were you able to figure that out? Were you able to figure out the right comparison to make? To check whether the size of this normal force makes sense. That's a good test as to whether you really are deepening your insight and understanding into these physics concepts as you move through the problems. If you realized on this problem that it makes sense to compare the normal force to Jessica's pushing force, that shows that you've made some good progress in deepening your insight into the concepts. And on the other hand, if you just kind of blindly compared the normal force to the weight force for this problem, that would indicate that you're working too much on autopilot when you thought about those issues. Moving on, what can we do with this result? Well, we can substitute this result into the y component for Newton's second law. Let's try that. We could do the calculation on the left-hand side in one step, but I'll split it. I'll figure out this separately just so we can compare these forces at some point maybe and get some more insight here. So we have 0.3 times 111.3. There's plus and minus signs here, so be extra careful to get all the plus and minus signs copied correctly in each line. Notice that now we're down to one unknown. Now the equation has only one unknown, so it looks like we can make some good progress by continuing to solve this equation. All right, now we can use the calculator to simplify the left-hand side. Negative 117.6 minus 33.39 plus 178.1. So that gives us 27.11. All right, so then we have here 27.11. Let's divide both sides by 12 to get the variable by itself. Because this is a 9, I'll round this up to a 6, 2.26. And let's pause with this intermediate result. Let's put in some units. The SI units for acceleration are meters per second squared. Did the answer come out, did this result come out positive or negative? Mathematically, this came out positive. Does that make sense? Well, let's try building the acceleration into our sketch to see whether that makes sense. So a positive acceleration would be an upwards acceleration. Our positive y direction is up, so the acceleration is pointing up. Remember that a sub x was 0. Since a sub x is 0, if the y component is pointing up, then the overall acceleration is pointing up. Let's build that into the sketch. So here's this upward acceleration vector built into the sketch to reflect the positive a sub y. Does that make sense? Well, remember the object started at rest at this point, and then it started moving upwards. So it makes sense that the acceleration should be upwards to change us from a velocity of 0 to an upwards velocity. Remember that by itself, the direction of the acceleration vector does not have to match the direction of motion. But since the object started from rest, the direction of the acceleration vector in this problem does indicate what direction the object should begin moving. We started at rest, so we need an upward acceleration in order for the object to begin moving upwards, to change the velocity from 0 into an upwards velocity. The acceleration causes changes in velocity, and we need the velocity to change from 0 to up. So we need an upward acceleration for that. So that does make sense. Now, continuing to think about it, what do these results here mean? Well, remember the direction of the velocity vector indicates the object's direction of motion. So we know that after time 0, the object is moving, sliding up the wall. The object begins at rest and then moves up. It begins at rest because the initial velocity is 0. Then it moves up because the later velocity is pointing up. And as it moves up, it's moving up with increasing speed. We know that because our acceleration vector is parallel to the velocity vector. And when acceleration and velocity are parallel, the object is moving with increasing speed. So at time 0, the acceleration changes the velocity from 0 to an upward velocity. And then afterwards, the acceleration keeps changing the velocity to point more and more in the upward direction, increasing the speed. The acceleration reflects the changes in the velocity. Well, I think this makes sense. This result that we began at rest and then move upward with increasing speed, this is all consistent with the information that was given in the problem. It would not make sense if the acceleration was 0. If the acceleration was 0, we would just stay at this point, stay motionless at this point. And it would not make sense for the acceleration to be downwards. If the acceleration was downwards, we would start at this point and then get dragged in a downwards direction. So the positive acceleration does make sense in this case, and all these interpretations are consistent with what's given in the problem. So we've seen that the sign of this result makes sense. This result came out to be positive, and we've seen that that makes sense. In fact, if this result had come out to be negative, we would know that we'd made a mistake. Well, remember, it's a good idea to always emphasize when components are positive by putting a plus sign in front of them. So I'll emphasize that this came out positive in this component by putting a plus sign in front. The sign of this component makes sense. What about the size? What about the size or the magnitude of this result? Does that make sense? Well, on some of the previous problems, we've compared the acceleration to 9.8 meters per second squared. But that is not really a logical comparison to make on this problem. On this problem, a sub y could logically have come out to be either smaller or bigger than 9.8 meters per second squared. So it's not really particularly logical to compare this result to 9.8 meters per second squared on this problem. Do you see why? Well, remember that 9.8 meters per second squared is the magnitude of the acceleration that would be caused by the full weight force. The magnitude of the acceleration that's caused when the only force on the object is the full weight force is 9.8 meters per second squared. But this acceleration really isn't being caused by the weight force, is it? Remember that the acceleration in this problem is upwards. The acceleration is upwards, and that upwards acceleration is being caused, remember, by the y component of Jessica's pushing force. It's Jessica's pushing force that's causing this upward acceleration. Of course, Jessica's pushing force is being partially canceled by friction and the weight force. But it still makes sense to say that the upward acceleration is being caused by Jessica's push, not by the weight force. After all, the weight force is pulling down, so a downward weight force couldn't cause an upward acceleration. The fact that the acceleration is upward is a result of Jessica's pushing force, not the weight force. Since the acceleration in this problem is being caused by a pushing force and not by the weight force, there's no logical reason to compare this number with 9.8 meters per second squared. So that's not a particularly interesting comparison, so we won't make that comparison on this problem. We'll just say that does this seem like a roughly reasonable size? Is this in the same range of sizes as the accelerations that we've gotten on previous problems? Yes. The size of this acceleration is in the same range as the accelerations we've gotten on previous problems. So that seems reasonable. If we had gotten an acceleration of, say, positive 22 meters per second squared, that would be actually quite suspicious. This isn't logically impossible. There's no logical reason why this couldn't happen, but this is just a larger acceleration than you would usually get for this type of problem. This is a larger acceleration than you would usually get for the setup in this type of problem. This would require a very strong push from Jessica. This would require a suspiciously large push from Jessica. So it's not impossible, but it's large enough that it would be suspicious. On the other hand, an acceleration of around 2 meters per second squared is definitely in the same range as the accelerations we've gotten on similar problems in the past. And that gives us some more confidence that we haven't made a mistake yet. Let's do some more work to see if the collection of our results so far makes sense. Now we know that on this problem, the object began at rest in both components. The object began at rest in both components. Let's think now about the x component. So in the x component, we know that the x component of Jessica's pushing force will be canceled by the normal force. That's why I tried to draw these two arrows the same length, so that there will be zero net force in the x component. Zero net force in the x component, because the normal force will cancel the x component of Jessica's applied force. But the force determines the acceleration, so there will be also zero acceleration in the x component. Now remember that if an object begins at rest, then it has a natural tendency to remain at rest. Since there's zero net force in the x component, the object will obey its natural tendency and will remain at rest in the x component. That's consistent with our knowledge of this problem. We knew the object would be moving vertically, it would not be moving horizontally. It remains at rest in the x component because it began at rest in the x component and there's zero net force in the x component, so it obeys its natural tendency to remain at rest in the x component. Or using the acceleration, remember the acceleration tells us how the velocity is changing. Since a sub x is 0, that tells us that the horizontal velocity is not changing. Well, the horizontal velocity started at 0. The horizontal velocity started at 0, and it's not changing, so the horizontal velocity stays at 0. The object remains horizontally motionless. That all makes good sense. We used the idea here that the net force determines the acceleration. Now, what about in the y component? Well, we know that the object also began at rest in the y component. But we know that Jessica's pushing force is attempting to start the object moving upwards, sliding up the wall, and we know that apparently that's going to succeed. The object does start moving up the wall. So there must be a net force y that points up the wall to start the object moving. Apparently net force y points up at time 0, which explains why the object begins moving at time 0. Now we know that Jessica's push is pushing up, and we know also that Jessica's push is being opposed by the weight force. And we also know that Jessica's push is being opposed by a downwards frictional force. So apparently Jessica's upward push is outmatching the combination of the downward weight force and the downward frictional force, so that overall net force y points up at time 0. So the object began at rest in the y component at time 0. Its natural tendency would be to remain at rest at time 0. But since the object actually began to move, at time 0, there must have been some net force that caused it to begin moving. And that net force must be being created. There must be an upward net force at time 0 that's created because the upward pushing force is outmatching the downward weight force combined with the downward frictional force. Now, once the object begins moving up, its natural tendency would be to continue moving up. But the natural tendency would be to continue moving up at constant speed, whereas we know that in this problem the object is actually moving upwards with increasing speed. So we need to explain that increasing speed after time 0. And again, that must be explained by an upwards net force in the y component. There must be an upwards net force in the y component after time 0 that explains why the acceleration points up after time 0, which explains why the object is speeding up, giving us an acceleration that's parallel to the velocity. Well, again, we have an upward force from Jessica's push, and that's being opposed by the downward force of the weight and the downward force of friction. And apparently Jessica's upward push is outmatching the combination of friction and the weight force. And we can confirm that from our work here. Here's the magnitude of Jessica's upward pushing force. And you can see that that is being opposed by the downward weight force. Notice that this actually represents the entire magnitude of the weight force. And it's also being opposed by the downward frictional force. And again, this actually represents the entire magnitude of the frictional force, because the y component has the same magnitude as the overall frictional force. And you can see here that Jessica's upward pushing force is big enough to outmatch the combination of the downward weight force and the downward frictional force. If we combined negative 117.6 and negative 33.39, it's pretty obvious that that's still going to come out to be less in magnitude than 178.1. That's what Newton's second law figured out for us. That's why Newton's second law told us that a sub y was going to come out to be positive. Newton's second law figured out that the acceleration would come out to be upwards because Newton's second law saw that the net force was going to come out to be upwards because of the relative sizes of these three numbers. As usual, we didn't have to think about the relative sizes of these three magnitudes when we were first solving the problem. And in fact, it's probably better not to try to predict these magnitudes because it might be confusing. But now that we've gotten some results, it's good to step back and ask whether our results make sense. So now's a good time to think about the relative sizes of these numbers and check that they came out to numbers that make sense. And they do make sense. It makes sense that the upward pushing force is outmatching the frictional force and the weight. That explains why the objects, we have a upwards acceleration in this problem. By the way, notice that the weight force on this problem turned out to be a lot bigger than the frictional force in magnitude. The weight force turned out to be a lot bigger than the frictional force in magnitude. Maybe I'll go back and adjust my free body diagram to reflect that. Okay, so I adjusted these lengths in this version of the free body diagram to show, I'm trying to show here that the magnitude of the weight is greater than the magnitude of the frictional force. So I drew this weight arrow longer than this frictional force arrow. And also I want to show that the magnitude of the y component of Jessica's pushing force is greater than the combination of the friction and the weight. So I tried to draw this arrow. I tried to draw this arrow for the y component of Jessica's pushing force. I tried to draw this arrow longer than the combined length of the friction arrow and the weight arrow, just to give us a little bit more intuition for the relationships between the forces on this problem. Again, you should not worry about those relative lengths of the arrows when you're first drawing your initial free body diagram. That's just something to do when you're getting results from the problem to help you summarize your results so you can see if the results make sense. Okay, so this object begins at rest in both components. There's zero net force in the x component, so the object obeys its natural tendency and remains at rest in the x component. There's an upward net force in the y component, so that upward net force causes the object to overcome its natural tendency to remain at rest and to instead begin moving upwards in the y component, and then continuing. The continued upward net force causes the object to overcome its natural tendency to move at constant speed, so instead the object that's moving upwards will be moving upwards with increasing speed because of the continued upward net force after time zero. Okay, so I think we've done the work to see that all of our results so far do make sense. As usual, this type of analysis shows the importance of thinking in terms of components. Our analysis for the x component is quite different from our analysis for the y component. And it also shows the importance of giving a careful label to all the concepts. What I have written now is useless. It's useless to say things that are pointing up or left or right or down, or they're equal to zero. It's useless to make all those statements unless you give a careful label to say who's pointing up, who's pointing left, who's equal to zero. So don't use the word it. Make sure you use the exact right symbol or the exact right name both in your thoughts and on paper, to label every concept that you're thinking about. Here's the useful version where every single direction and number is labeled. Now what? Well, we've got this acceleration, and now we're going to pull that over to our kinematics framework. Remember, we had already said we needed a sub y. Well, now we've figured it out. We don't need it anymore. We've figured it out. So we can plug that in here. Now we know a sub y. Our a sub y now is going to be 2.26 meters per second squared. And now notice that we have 3 knowns. Now we know 3 numbers. But when you know 3 kinematics values, that's when you're ready to choose a kinematics equation. So let's go through the process of choosing a kinematics equation. Now, we want an equation that includes these 3 known values, and we also want to pick an equation that has v final y, because that's what we need to figure out. So the variable we don't care about here is delta t. We need to pick the kinematics equation that's missing delta t. Remember, we're using this box of equations because this is the box with constant acceleration and changing velocity. But did you notice we should be picking a y equation? I believe that in the previous videos we were using the x equations. But in this problem we're applying kinematics to the y component, so on this problem we're picking one of these y equations. Again, we decided we want to pick the y equation that's missing delta t. So here it is. Here's the equation that we should be using. Remember to write the general formula before you plug in. That'll be v final y squared equals v initial y squared plus 2 a sub y delta y. Now we plug in. Remember to try to write down the exact right symbols, including the exact right subscripts. So our v final y we don't know, but the specific symbol we're using that is v sub 1y. Don't forget to square it. V initial is 0. A sub y is the new number that we figured out. Oh, so I guess I should follow my advice and put in a sign here. Remember that components should get plus or minus signs. This came out mathematically to be positive, and I'll emphasize that by putting a plus sign here. And we saw that that positive sign made sense. So again, over here, I can write this with a plus sign to emphasize that it came out positive. But when I write it in the equation, I'll leave out the plus sign to make the mathematics a little bit simpler. And our delta y is 1.2 meters, and again I'll leave out the plus sign and the units just to make the math a little bit easier. So this probably, hopefully, will not be one of the hardest equations that we've ever solved. So we can do this calculation. 2 times 2.26 times 1.2. If we type this calculation into the calculator exactly the same as it's written on the page, we can trust that we can do that in one step rather than breaking it up into steps. Okay, well, it should be apparent here that since this variable squared is 5.424, that means the variable is the square root. Now, every number has both a positive and a negative square root. So when you take a square root, you need to decide, do I want to take the positive square root or the negative square root? Well, we know that this object should have an upwards velocity. The object has an upwards velocity. That's our positive direction. So we expect the y component to come out to be positive. So to get a positive y component, we want to take the positive square root. Well, that's what the radical sign means by itself. by itself, a radical sign means the positive square root. So we can just continue to write this like so to show that we're taking the positive square root. There are some situations in physics where you have to take the negative square root. So you do have to pause and think about that. When you take a square root, decide if you want the positive or the negative square root. But in this case, we wanted the simple result of the positive square root. So let's go ahead and work that out. I guess I'll round that to 2.33. This is digits in 8, so I'll call this 2.33. As usual, I'm not trying to get the exact right number of significant figures. I'm just trying to include enough digits so that you can check your own work against mine and be sure that you got the same result. Okay, there's our result, so we should stop to ask whether this makes sense. Well, we forced it to come out positive, so that makes sense. Oh, I guess I was careless here, wasn't I? These are not the correct SI units for velocity, are they? These would be the units for acceleration. These should be the units for velocity. Is there anything we can do to check whether the size of this answer makes sense? Well, there's nothing we can really compare it to. There's no velocities we can compare this to. We can just ask if this is a reasonable size for a velocity. That's hard to think about because we're not usually used to using meters per second in everyday life. But it's helpful to know that 1 meter per second is very roughly 2 miles per hour. So very roughly, the number of meters per second, the number of miles per hour is double the number of meters per second. So we could say here that this is this velocity is roughly 2 meters per second, which is roughly 4 miles per hour. The number of miles per hour should be double the number of meters per second. So is that a reasonable rate that for someone to push something up an inclined plane? I think so. It's a pretty fast push, I guess, but it's not unreasonable. So somebody could push a box up a wall at 4 miles per hour. I think that seems reasonable to push the box up the wall at 4 miles per hour. So, for example, I don't know if this had come out to be 20 meters per second. That would be roughly 40 miles per hour. That would seem suspiciously fast. That would be a heck of a push. It would take a heck of a push to push something at 40 miles per hour. That would be suspicious. And if it was coming out to, say, be 400 miles per hour, that would be extremely suspicious, and there'd be a good chance we'd made a mistake there. So there are some things that we can do just to check that the size of this answer is reasonable. There's nothing to really compare this to as a reference, but we can see that this is a fairly reasonable speed by roughly converting it into miles per hour. This is the comparison to make if you're from the U.S., where we're used to making conversions in to driving, to thinking about our driving speed in terms of miles per hour. I think that in most other countries, driving speeds are measured in kilometers per hour. So if you're from a country where driving speeds are in kilometers per hour, this might be a more useful conversion to use. The number of kilometers per hour is very roughly 4 times the number of meters per second. So you could use that to see, to get a feel for the size of how fast this object is going. Well, it's time now for us to actually come up with our answer to the question. I guess I should, we talked about why it makes sense that this velocity is positive. Remember, it's a good idea to put a plus sign in front of positive components so that you think about whether the sign is positive or negative and to emphasize the meaning of the sign. So we've discussed why it makes sense that this is positive. So I'll put a plus sign here to emphasize that this came out to be positive, just like we put a plus sign to emphasize that this component was positive. Now, the next step is to try to answer the question. Now, this is not exactly what the question was asking us for. Remember that the question was asking for the speed, which refers to the magnitude of the overall vector, not directly to a component. The question was asking for the magnitude of the overall vector, the overall speed. So the way to figure out information about the overall vector is to think in terms of the components. So what are the components at time 1? This is time 1 at the top of the wall. What were the components of the velocity? Well, we just figured out the y component. The y component of the velocity when we reach the top of the wall, as we just figured out, is positive 2.33 meters per second. And what's the x component? Well, the object is moving vertically. It's motionless horizontally. And therefore the x component is 0. Remember that we're using these axes. Well, when one component is 0, it's very easy to use the components to figure out what we need about the overall vectors. The magnitude here, since this component is 0, the magnitude of the overall vector is the same as the magnitude of the component. So that will be 2.33. As we've already discussed, this velocity is pointing straight up, no x component. So the magnitude of the y component is the same as the magnitude of the overall vector. And the question wasn't asking for the direction of the overall vector, but just for completeness, we might as well make a note that the overall velocity is pointing up because the x component is 0 and the y component points up. The y component is positive, so it's pointing up. So that's the direction of the overall vector, although that's not what the question was asking us for. The question was asking for this information. Notice that here I included a plus sign because components can theoretically be negative. But this is a magnitude, and magnitudes could never be negative, so there's no need to include the plus sign. We don't need to emphasize that this is positive. All right, and now we're ready to write our answer. So notice in this case, it was very easy to go from the y component to the overall vector. But I just wanted to write out the exact thought steps for that process, even though that should be quite easy. Remember to think carefully. First, we think about each vector oftentimes in terms of the components, and then we can put the components together to find the overall vector. But when one component is 0, then the overall vector is basically identical to the non-zero component. So finding v sub 1y for this problem was basically enough to find the overall speed. All right, so now we have our answer to the question. The speed when the block reaches the top of the wall is 2.33 meters per second. So we finished these steps for general one-dimensional kinematics. Remember that at the end of the problem, you should make sure you answered the right question and that you answered all parts of the question. Well, yeah, the question was asking just for the block's speed at the top of the wall. Some questions, so that's all we need for that. We've already checked that our answer makes sense. Make sure that you included units. So if you write your answer like this, it's wrong. An answer without units is wrong. Okay, this step is not relevant for this problem. So it seems like we finished the question. So let's review the important techniques and ideas that we used when attacking this question. So remember that you should regard this problem as a test of how much progress you've made of learning the techniques from this video series. Why is this a good test? This is a good test because on the one hand, this problem has a number of ways that it's different from the previous problems. In many ways, this problem was different from the previous problems. So why is it a good test? Why do I expect that you still should have been able to get it right? Because even though it's different, we've already learned in the previous videos everything you needed to know in order to adapt to the differences of this question. This is the first problem that we've tried where the object was moving vertically. We've done problems where objects were moving horizontally, and we've done problems where objects were moving up or down an inclined plane. But we've never done a problem before where the object was moving vertically. But you should have been able to adapt to that. You should have simply chosen a positive y-axis pointing in the direction of motion, and then used these axes to adapt to the details of this question. Now, as a result of the vertical motion here, part of what happened here is this is the first problem we've seen where the surface in contact with the object was on the side of the object rather than underneath the object. So in the past, we've seen normal forces that pointed up or that pointed kind of diagonally away from the surface of an inclined plane. This is the first problem we've seen where we had a normal force that was pointing horizontally. But if you used the simple rules that we've talked about before about how the normal force points perpendicular to and away from the surface, you should have been able to figure out and adapt this new normal force without having to overthink it. In all the previous problems, we had frictional forces that were horizontal or parallel to an inclined plane. This is the first problem we've had with a vertical frictional force. But again, you should have been able to adapt to that, just using the simple rule that the friction is parallel to the surface and opposite to the direction of sliding. So the components that we figured out for many of these forces were different in some details from the components we've seen on previous questions. I don't think, so in previous problems we usually had nx equal to 0, but here we had ny equal to 0. Previously we usually had the y component of friction equal to 0, and here we had the x component equal to 0. But again, you should have been able to adapt to that by using the techniques that we've already seen previously. I believe this is only the second problem where we had what we could call a kind of applied or pushing force. But you should have, hopefully you were able to adapt to that. That didn't introduce any particular problems. This is the first problem where we were given a force where the angle was identified with the vertical, like this. This is the first force we've seen where the angle was identified with the vertical rather than the horizontal. But if you follow the steps for SOHCAHTOA, you still should have been able to correctly break that force into its components. I think this is the first problem where we had to do a subtraction in order to figure out the displacement. We had to do a subtraction to figure this out, but that's something that you should have been able to figure out by drawing a large, clear sketch so you can see the relationship between the various distances in the sketch. So here are some of those principles that we've been discussing, and I hope you can see how this problem illustrates these. So this problem was somewhat different from the previous problems, but that didn't mean you had to wing it. I hope that you really feel now that there is a systematic process for attacking Newton's second law and one-dimensional kinematics, and that you can simply adapt that process to the individual differences of each problem. Even though this problem had a lot of differences from the previous questions, there was also many, many similarities in our overall approach. The general approach we took to drawing the free body diagram was the same as before. The general approach that we took for making the force table was the same as before. The free body diagram and the force table have the same general appearance as they have in our past problems. And our general approach to organizing the algebra for our three sets of equations here is the same as on previous problems. So our work for this problem looks very similar to the previous problems. We didn't wing it. We didn't have to overthink it, even though this problem had some differences. The normal force on this problem was a little bit different than on previous problems in its direction, and the same for the frictional force, but we didn't have to overthink it. We just used the simple rules for figuring out the direction of the normal force, the direction of the frictional force, and of course the direction of the weight, which was still down in this case. There were simple rules for applying SOHCAHTOA. We don't need to overthink that. There's simple rules for breaking the forces into components when we don't need SOHCAHTOA, and for using the axes to break things into components, and for doing the algebra. So we did not have to overthink it in order to adapt correctly to this problem. We simply had to remember the techniques and simple rules that we've used on earlier problems and adapt them to this problem. But of course, it's important that we not be on autopilot. There were some differences between this problem and the previous problem, and we had to pay attention to those and adapt our approach. So how did you do on this problem? Did you do well on this problem? If so, excellent. That shows that you've made some good progress. If you did poorly on this problem, you should go back and ask yourself what went wrong. Were you winging it? Were you not using the systematic approach? Were you overthinking it? Were you trying to think through things more deeply than was really necessary rather than just applying the simple rules that we've talked about before? Were you on autopilot? Did you assume this problem was similar to the previous questions without noticing the differences and adapting to them? Try to figure out where you went wrong and correct those mistakes so that you can do better on problems like this in the future. And again, if you did well on this problem, excellent, that's good work. But don't congratulate yourself too much because these are not, what we've covered so far in this video series is not the only types of problems that you can see when you're dealing with Newton's second law. So we've covered a certain set of problems that deal with Newton's second law, especially problems that deal with kinetic friction and kinematics. But there's still other topics that we have to go over, particularly problems that involve static friction. Obviously, still for static friction, we're going to use a lot of the same general principles as for kinetic friction, but there are also some differences. So there's still some important material to learn. Even if you've made good progress on kinetic friction problems, we still need to learn how to attack static friction problems. And I believe I'll begin with some problems like that in the next video in this series. And I'll just mention, I said that I think we've covered a lot of the basic techniques so far for attacking kinetic friction problems. And if you did well on this problem, then you have a good fundamental technique set up for attacking kinetic friction. But you shouldn't think that the problems we've covered so far have covered all aspects of kinetic friction that you could see on your exams. It is certainly possible to make kinetic friction problems that are harder than this one. And hopefully we'll get to work on some of those harder kinetic friction problems as well later in this series of videos. Did you find this video to be helpful? If so, you can support the videos by making a monthly pledge of $1 or more at my Patreon page. You can visit my Patreon page by clicking the link on the screen or by using the link in the video description box. Thank you.